Okay, any question? Today we'll also give you the meeting exam. Okay, in the teaching lab, the TA will paste out your midterm. Please go through the grading to see any question. You can ask the TA, and then you still have to turn it back, otherwise you won't have the score. Okay, let's finish the unit here. Sequencing method. Okay, for basic static CMOS design, and also the other circuit family, you could have the synchronous circuit like this. The flip-flop here, flip-flop here. So clock signal at the right edge will sample the input and update the flip-flop simultaneously. That's why we call that synchronous circuit. They update synchronously, okay, at the same time. So the new value of this will go through the common circuit. This could be more than one bit, okay? It could be multiple bit register. And after some combination logic, you're getting the output values waiting at the input of the next flip-flop, next register, until the right edge goes up. Until the next one edge, you sample the value and then you get it in, and so on and so forth. That's a typical synchronous circuit using the clock signal here. And another one is two-phase lag for sequencing. There are two non-overlapping clock signals, phi 1 and phi 2. Well, actually, before, these are also used in industry, but nowadays, the industry almost always use this kind of clock signal, okay, only single phase. Because a long time ago, they worried about class Q, they worried about grid condition, but eventually they solved all the problems. So the synchronous circuit using one phase clock signal is almost dominating the whole design community. Okay, but still you can just learn the design style here. For two-phase clock signal, phi 1 goes up, phi 2 goes up. But we notice that there are some period which is both low, meaning these two phases will not overlap each other. They will not be on simultaneously. Even furthermore, there is a period of time they are both low. Try to separate it. Because of, if there's a class Q, if phi 1 arrives later than you expect, it was, you still have a lot of room, you still have a lot of space. It will not overlap with phi 2. So in the first half, phi 1 clock signal goes up, you get in after some delay, you get new value, you go through the combination circuit, waiting for phi 2 goes up the right edge. And after that edge, you go through another conventional logic. So you can imagine that this conventional logic will be divided into two halves. You cut into two halves. And the first half will be here, the second half will be here. Okay. So this is kind of two-phase transparent lab design style. There are two-phase clock signal. But again, as I said, it almost has already abandoned in industry. So this one is the most popular design style. Another one is for high-speed circuit design. Not very popular, but in some application, people might need that design structure. We call that path latches. The flip-flop, the two-phase, the path latch. This one is the most popular one, okay? And almost abandoned it. It is sometimes we might use it. But again, it's not very popular. Some applications might use it. How does it work? Again, there's only one clock signal, like this. But we don't use flip-flop. We use simply latch, level sensitive latch, But the clock signal only goes up high in a very short period, and then goes down for most of the time. And then goes up very short period, goes down like that. But why does it work? Can you see that? Can you imagine why this circuit works? This is not flip-flop. Why some people might prefer that? Because that is much more simpler than flip-flop. Flip-flop, you need stage, right? Master slave. For that, only one stage. So this circuit is more simple compared to here. And also, when the clock signal goes up, during the time period, clock signal is high, signal goes through the latch. And then when it goes through conventional logic, there's no delay. And then when it goes up again, it will be entering the second latch. However, you should be aware that there could be an issue if the clock signal is high, the period if the delay is very short delay, you could get problem. Why? Let's say there's only one inverter, and that delay very short. That could have problem. Why? Because when it goes up, God is high, you entering the latch, it appears here, and we're still high. It's already around here, and it might go through. When you are still high, you can affect this latch, or you might have not enough hold time. We mentioned that before, right? Hold time. You could have a hold time failure because the signal goes through quickly and then update the value here, and that will affect this latch when we are still in the same clock period. So in this kind of design style, you have to be careful about the period here and the delay here. It's very short, such that it can enter the latch, but it should not be too long. It should not be stay too long, because we are worried about it might go through the conventional logic too quickly, and then it affects the next latch. But the circuit is small, and it could be very fast. Any question? All right. I guess we finished this unit. Just summarize. For clocking design, flip-flop, very easy to use, supported by all tools. The most popular one, flip-flop, stage CMOS, and also flip-flop. They are very popular. And two-phase transparent latch, two-phase clock. It can allow clock skew, but as I mentioned, it's not very popular nowadays. Pulse latch very fast and very small, but you have to be aware of the hold time value, hold time risk. Okay, so we are done with Unit 4. And I mentioned next week we are going to have a quiz. It will cover Unit 4 and Unit 5. Unit 4 and Unit 5 here. Let's get to Unit 6, their path. Now we are trying to design some subsystem, not just basic component, basic circuit, but the circuit will go larger and larger and larger. There are paths. we will introduce adder design, converter, shooter, multi-input adder, and multiplier. These are all used in their test in the CPU design, especially ALU. They are all conventional circuit. Single bit addition. The 2-bit adder, okay? Actually 1 bit plus 1 bit, okay? 1 digit, one bit adder, and there are 2 input A and B, giving you sum and carry out, right? So that's the truth table for the input and output. When both are 0, you get sum 0, carry out 0. 0, 1, you get sum 1, carry out 0. 1, 0 again, sum 1, carry out 0. Only 1, 1, you get a carry out, right? 1 plus 1, you get 1, 0. But that's for half adder. For full adder, you need 3 input bits. A, B, and C. C is carried in, okay, from the low bit position. And in the truth table here, 0 plus 0 plus 0, you get 0, 0. If there's only 1 bit, it's 1. You get 0, 1. Okay? And 2 bit 1, you get 1, 0. Okay? 2 bit 1, 1, 0. 3 bit 1, you get 1, 1. So that's a typical full adder with 3 input. And for the Boolean function, for half adder, sum is equals to again, right? 0, 1, 1, 0, you get 1. That's equals to 1, 0, 1, 1. And carry out, only both are 1, you get carry out 1. So that's AND gate. Equals to again, AND gate. For full adder, sum again, if you have even odd number 1, you get 1. So that equals to a gate. 3 input equals to a gate. For example, here, and here. When you have only 1 in position 1 input 1, or you have 3 input 1, you get some 1, right? That's equals to a gate. For carry out, when you have the output 1, your 2 bit, 3 bit. So that's a majority voting circuit. Majority, right? Just voting. If more than half have 1, you get 1. So 3 bit input, 2 of 3 have 1, you get 1, right? So that's the majority. 像投票表决一样，多数决1就是1。Which is more 0, more or 1 more. If you have more 1, then you get 1 and carry out, right? So that's the majority circuit. But how do you write a Boolean function for CR? Can you give me the Boolean function? What's the Boolean function? It should be easy. A, B, or B, C, or A, C, or A, B, C. Just based on the Boolean function, the truth table is right here, and here. There are 4 product terms, and all them together. But we found out actually it can be simplified. You don't really need this term. Is that right? Why? Why is that? Boolean function formula A or AB equal what? How do you simplify it? You will get A. Okay. So A, B, or A, B, C will equal from the set theory point of view, 集合论 A and B, okay, A here, A and B here. This actually cover A and B from the set theory point of view. This is A, this is B, this is A and B, right? The channel region is A and B, right? And A or, this means union. A, union, A and B, you still get A, right? So that's why A and B and C can be omitted. So AB, A gate, BC, A gate, SA, and altogether you get the carry out. And for equal gate, well, try by yourself. Should not be difficult to write down the Boolean function for the equal gate. For two input, should be easy. A, B bar, or A bar B, right? 1 0 1 1 0 1 or 1 0. They'll give you the carry out. But for three input, you have what? Odd number 1 in input. You can try to write down the Boolean function and try to simplify it. So, the homework, I want you to design a 4-bit adder. So there are 4 adder, okay? So this is a 4-bit adder. Pre-design the 4-bit adder using the basic logic gate, like inverter, AND gate, NAND gate, or NOR gate, OR gate, this kind of logic gate. Pre-design the 4-bit adder. Is that okay? In the first part of the work. Okay, let me give you the Boolean function for the carry out here. Again, like I said, from the digital logic design formula, you have 4 product terms, right? I'm sorry, for carry out. Okay, for sum, right? We are talking about sum. 1 here, 1 here, 1 here, 1 here. So here, here, and here, and here. The sum will be equal what? A bar, B bar, C, right? And A bar, B, C bar. Okay? A bar, A, B bar, C bar. The last one, A, B, C. Okay? There are 4 product terms. And you might want to simplify that. You might minimize the Boolean function. You could use like some kind of like column map. Remember that? Column map can minimize the circuit. The string input Boolean function, you can minimize the circuit using column map. But for the homework, I don't require that. Even using the complex circuit, fine, it doesn't matter. As long as the circuit works, you pay for the homework, right? 就你不一定要用4去把它解放没关系，最低分作业你只要能够做得出来，可以 work， 我们就算通过。 I'm going to stop at this moment. Let's try to go to downstairs. Just go to teaching lab B204。我们去这个教育实验室啊。And if you look at the inner system, just look at the inner system. We have uploaded some files. Please download them. In the first area here, there are 3 files. Please download to your PC. You can work on your homework on your PC at home using the tool, right? And the TA will give you a tutorial how to use that. So let's try it. And if you have enough time, try working on the simple design like multiplexer. You can borrow the example from the lecture file. Try to design two input multiplexer, try to simulate them, and make sure that your design is verified. Okay, let's go to the 204. 这个可以帮我双号。